Hello, Math 2. This is Unit 5, Lesson 5. This lesson is quite a bit different from the others. We're going to be focusing on special right triangle patterns. This is the last lesson in Unit 5, so the review and test are coming up very, very, very soon. If you're a little behind on this unit, make a plan to get caught up. So we are going to start by drawing a diagonal in a square. So I've got a perfect square here. If we draw a diagonal in this square, we have formed two triangles. Because this is a square, we know that these two sides are the same length. And because the original shape is a square, we know this is a 90-degree angle here. So we have formed two right triangles. They are both isosceles right triangles, which means that their two sides have the same length. So they're isosceles right triangles. That since they're isosceles, we know that their angles here and here are the same, and they are 45-degree angles. So we're going to think about these triangles a little bit more. So if we've created a right triangle with two legs that have the same side that each have 45-degree angles, we're going to use the Pythagorean theorem to calculate the hypotenuse, which was the diagonal in our square. So 8 squared plus 8 squared is equal to c squared. That's 128 is equal to c squared. And when we take the square root, we get 8 root 2 as our hypotenuse. Well, here's another one. We've got a 45-degree angle. It is another side that's length 3 and another 45-degree angle at the top. So if we do the Pythagorean theorem, it's 3 squared plus 3 squared equals c squared, and that is 18 is equal to c squared. And if we take the square root of both sides, we get 3 root 2. And I've got one more. We've got an isosceles right triangle here with the side length of 1. This other side also has to have length 1. Those are 45-degree angles. If we do the Pythagorean theorem, it's 1 squared plus 1 squared is equal to c squared. So that's 2 is equal to c squared. And if we take the square root of both sides, we get root 2 as our hypotenuse, or 1 root 2 if you want. So do you notice a pattern? Are you seeing a pattern? You might be noticing that the hypotenuse is just the length of the leg multiplied by the square root of 2. This one had legs that had length 3. The hypotenuse is 3 root 2. This one had legs of length 1. The hypotenuse is 1 root 2. That is our special 45, 45, 90 triangle. So in a 45, 45, 90 triangle, the hypotenuse is always root 2 times the length of the leg. And the legs are the same because it's isosceles. So if you want to know the leg, since we know that the leg multiplied by root 2 gives us the hypotenuse, if we were solving for the leg, I guess, we would divide by root 2. So the leg is equal to the hypotenuse over root 2. If you needed to sort of work backwards. So I'll show you what I mean. So in this triangle, it is isosceles. This leg is also 18. This is a right triangle, so this is a 45, 45, 90 triangle. So we know that the hypotenuse is the leg multiplied by root 2. You might be wondering, we've done all this right triangle, SOHCAHTOA trig. You might be wondering, well, couldn't I just use that? And the answer is absolutely yes. You could have, instead of sort of just memorizing this special right triangle pattern, you could have always set up a ratio. For this one, we would maybe do the sine of 45 degrees equals 18 over x. So x is equal to 18 over the sine of 45 degrees. And you type that in your calculator and you're going to get 18 root 2 for the hypotenuse. So you can absolutely set up a trig ratio to solve for any of these sides. Special patterns are really just common triangles that come up a lot. They come up a lot in calculus, they come up a lot in trigonometry, and instead of having to do all this work of solving an equation, once you've seen enough of these, you just start to memorize them and it saves you time. So that's why we use them. So if I have a right triangle, isosceles 45, 45, 90 triangle, and I know that the hypotenuse is 5 root 2, then without setting up an equation, I know that each of its legs are 5. I could find that more formally if I wanted to take that hypotenuse and divide it by root 2, which leaves me with just a 5. Now in this equation, or in this triangle, the hypotenuse has a length of 12. So to get the leg, I have to take the hypotenuse and divide it by root 2. Now that may be difficult to do in your brain, but your calculator is certainly very adept at that. And if you type into your calculator 12 divided by root 2, your calculator will tell you that it's 6 root 2. And so those two legs of that special right triangle are 6 root 2. Even if the legs or hypotenuse are not integers, if they're fractions or radicals, our process is the same. Whatever our leg is, we multiply by root 2 to get the hypotenuse. So 1/3 times root 2, your calculator may report it to you like this. Or you can leave it as 1/3 times root 2 is fine as well. In this case, the leg has a length of root 10. So to get the hypotenuse, it's the square root of 10 times by the square root of 2. And your calculator, that is the square root of 20. Your calculator will simplify that to be 2 root 5. So the hypotenuse of this one is 2 root 5. In this special 45, 45, 90 triangle, I have root 6 as the hypotenuse. Since we want the leg, we're going to divide by root 2. Whoops. So this will be a root 6 divided by root 2, which is root 3. So the two legs each have a length of root 3. Okay, that was our first special pattern. So this is going to give us our second special triangle. We want to draw an altitude in this equilateral triangle. So we know all three sides of this triangle are the same. So an altitude is when you start at the top vertex of the triangle and you draw a line straight down at a 90-degree angle. So I have created here a 90-degree angle because it is an altitude. So when we draw this altitude in an equilateral triangle, we create two right triangles. An equilateral triangle that we started with has three angles that are all the same. The triangle angles always add up to 80. So each of those original angles was a 60-degree angle. The one on the top, though, gets cut in half. So we've got a 30 and a 30 at the top. So we have 30 and 60-degree angles in these two triangles. And if we're thinking about this triangle maybe on the left, this leg down at the bottom is half of that side. So the short leg, but this hypotenuse is the same side as the whole side of the equilateral triangle. So the short leg, and this is kind of hard to word, but the short leg is half of the hypotenuse. Okay, so we're going to try to use some logic and the Pythagorean theorem to calculate the unknown side lengths in each of our right triangles. So use the logic part of it is that if you remember our equilateral triangle, this whole side had a length of 10, which means this side of our right triangle right here is 5 because it's half. That 10 was broken into two pieces. So I kind of have the ghost of the equilateral triangle there to remind you. Okay, so we have a hypotenuse of length 10, and we have a side length at the bottom with length 5. If we do the Pythagorean theorem, I'm going to call this x. It would be leg squared plus other leg squared is equal to the hypotenuse squared. We're going to subtract the 5 squared. Now make sure you don't do 10 minus 5. This is not 10 minus 5. This is 10 squared minus 5 squared. So x squared is equal to 75. And if we root both sides of that equation, we get x equals 5 root 3. Here's another triangle. It has a short leg of length 10. So that means the hypotenuse, because this was half of the side of the equilateral triangle, that means the hypotenuse here must be 20. So if we did the Pythagorean theorem, this would be 10 squared plus the other leg squared is equal to the hypotenuse squared. If we subtract the 10 squared, and remember that is not 20 minus 10, that is 20 squared minus 10 squared, we get x squared equals 300. And taking the square root of both sides of our equation gives us x is equal to 10 root 3. So do you see the pattern there? We have 5, 10, and 5 root 3. We have 10, 20, and 10 root 3. This is our 30, 60, 90 special triangle pattern. In a 30, 60, 90 triangle, the hypotenuse is twice as long as the short leg. The long leg is the square root of 3 times as long as the short leg. If you're working backwards, you just divide instead. So if I had the short leg, I would times by 2 to get the hypotenuse. If I have the hypotenuse, I would divide by 2 to get the short leg. If I have the short leg, I times by root 3 to get the long leg. If I'm working backwards, I would divide by root 3. So in this first triangle, I know the short leg is 7. That means the hypotenuse is twice that, so the hypotenuse is 14. The long leg would be 7 root 3. On this next triangle, the hypotenuse is 16, so the short leg is going to be half of that. We're going to divide by 2 to get 8, and then the long leg would be 8 root 3. If the long leg is 4 root 3, that means the short leg has to be 4. More formally, I'm taking that leg and dividing it by root 3, which leaves me with a 4. And to get the hypotenuse, I just double the short leg. So when you're working with the 30, 60, 90, that short leg is really important. You never want to go directly from like the hypotenuse to the long leg or vice versa. You always want to go to the short leg first. Okay, this is by far one of the most complicated situations for a 30, 60, 90. I have the long leg and it's 12. I don't want to divide by 2. This relationship here is the the doubled relationship. The long leg is a root 3 relationship. So since I'm working backwards towards my short leg, I'm going to take that length and divide it by root 3. You can do that in your calculator, and your calculator is going to give you 4 root 3 as the short leg. And so now that I have that length, now I can times it by 2 to get the hypotenuse, which will be 8 root 3. Okay, we just have a couple more scenarios. In these scenarios, we have to decide which of our special patterns to use and then to use that pattern to solve the problem. So this says, what is the area of an equilateral triangle with a side length of 20? Well, the area of a triangle is 1/2 the base multiplied by the height. Well, we have the base is 20. We need the height. So I'm going to call that h. Well, the base is 20. We need to calculate h. Okay, so if this was an equilateral triangle to start with, then this portion of the edge of the triangle would be half of it, which is 10. And this is a 60-degree angle. This is a 30, 60, 90 special right triangle. The short leg right here at the bottom is 10. That means the height is 10 root 3. So now we can calculate that and get that the area is equal to 100 root 3. You can type that all into your calculator to get that. Or if you needed a decimal, it is approximately 173.2. Okay, next question. A square has an area of 49 centimeters squared. What is the length of the diagonal? Well, we're going to definitely be applying our 45, 45, 90 triangle pattern here. If the area of this square is 49, that means the two sides are each length 7, because 7 times 7 gives me 49. Well, this is a 45, 45, 90 triangle, and that means our special pattern of multiplying by root 2 will give us the diagonal. So the diagonal is 7 root 2. All right, last one. In the figure below, we've got a square, and this is the center of the circle. If the radius of the circle is 5, what is the area of the square? Well, since that's a square and this is the diagonal of the square, this is a 45, 45, 90 triangle. So if the diagonal is 5, we're kind of working backwards here. So the side length of the square would be 5 divided by root 2. And the two sides of the square are the same because it's a square. So we've got a square whose edges or whose sides are 5 root 2. Well, the area of a square is the length times width. So that's a 5 over root 2 multiplied by a 5 over root 2. And if you multiply that together, you get 25 halves. So that is the area of our square. All right, so special right triangles are a little weird and challenging at first. You just have to get used to using those patterns, and you need lots of practice. So the assignment has several to practice on. Let me know if you have any questions. And if you are getting stuck with your special triangles, you can always set up a SOHCAHTOA ratio to help you solve for the unknown sides. Thanks a lot.